Question 1. A glider is an aircraft with no engine. To be launched, a glider is uniformly accelerated. Now, before we go any further, whenever you see the words uniformly accelerated, it usually means that you can use the equations of motion. So you're going to be using the SUVAT equations from rest, and that tells us that the initial speed is 0, by a cable pulled by a motor that exerts a horizontal force on the glider throughout the launch. The glider reaches its launch speed of 27 metres per second after accelerating for 11 seconds. Assume that the glider moves horizontally until it leaves the ground. Calculate the total distance travelled by the glider before it leaves the ground. This is a calculate question, and we're going to use the solve smart method. The first thing we do is identify the correct section of your data booklet, and this is kinematics. It's equations of motion, it's projectile motion. So head to the kinematics section or the motion section of your data booklet. Then it's symbol. Write down the data given with the associated symbols. We know that u is equal to 0 metres per second. We know that v is equal to 27, time is equal to 11 seconds. We also want to calculate what s is. Okay, so we head then to set up the correct equation. Which equation in our data booklet involves these quantities? Well, the equation we're looking for is s equals u plus v t over 2. And then we substitute over 2, and that gives us an answer of 148.5. That's us substituted and solved, but now we need to look at sig figs. Each piece of data in the question is given to 3 significant figures. And we want to give our answer to the number of significant figures that's least shown in the question. So we want to give our answer to 3 significant figures. S equals 149 metres. And I like to underline the final answer to show the examiner this is the one I want them to look at. Question 2. 2 students are throwing a ball to each other. Student A throws the ball with a velocity of 11 metres per second at an angle of 36 degrees to the horizontal. The ball is released at a height of 1.6 metres above the ground. The ball passes over the head of student B and lands on the ground at point Q. The effects of air resistance can be ignored. A little tip here. When air resistance is mentioned, it's usually looking at SUVAT equations or projectile motion. So that gives us a little bit of a tip about what section of the data booklet to look at. Calculate the horizontal component of the initial velocity of the ball. We want to know what the horizontal component is. We know that the initial velocity is 11.0 metres per second and the angle is equal to 36.0 degrees. Head to our data booklet. We're looking at the horizontal component of the vector. So it's UH equals U cos theta. That's us found our setup. We now have to substitute in the data. Then we've got to solve, so pop that into the calculator, and that gives us 8.90 metres per second. I want to just check the significant figures. This is given to 3 significant figures. This data is given to 3 significant figures. Therefore, our answer is 3 significant figures. And just to be clear to the examiner, we'll underline the final answer. B, calculate the vertical component. We want to know the vertical component. Again, our data is U. Probably don't need to write this out again, to be fair. Just trying to show you the process. Head to the section of our data booklet. We're looking at the same section. It's kinematics, components of vectors. Our symbols are written down the left-hand side. Our setup for the right equation is UV equals U sine theta, because it's the vertical component this time. Then we substitute in the data. And we solve, which gives us an answer of 6.47 metres per second. Again, that's the 3 significant figures, and we know the sig figs, so let's underline and tell the examiner we're finished. The ball takes 1.53 seconds to travel from student A to point Q. Calculate the horizontal distance travelled by the ball. First things first, we're looking at horizontal distance. It's a projectile. So the section that we want to go to in our data booklet is projectile motion. The next step in our Solve Smart method is symbol. What symbols do we have that will help? Well, we want the horizontal distance. We want to know what that is. And that's different from the vertical distance. We're not going to give that the symbol S. We're going to just say distance equals. We know that the horizontal speed, we calculated that before, is equal to 8.90 metres per second. We know the time is equal to 1.53 seconds. And now what we want to do is set up. We want to set up the correct equation. And in this case, the correct equation is speed equals distance over time. Why do we use speed equals distance over time instead of the Suvat equations? Well, this is horizontal component of the velocity of the ball. The horizontal component does not change. It's a constant speed. So we can't use the Suvat equations. There's no acceleration there. So we're using the speed equals distance over time. And we rearrange distance equals speed times time. Substitute is the next section, 1.0, and solve. And we solve that to 13.6 metres. That distance, again, should be to 3 significant figures because all the data is to 3 significant figures. Underline it to tell the examiner we have finished. Question 3. In a game, a child throws a ball at a flat vertical wall. The ball rebounds from the wall. The child wins the game if the ball lands within a circular ring placed on the ground. And we've got 2 diagrams here. Whenever you see the word rebound or collides, I start thinking about momentum because explodes is another word. We're thinking about the topic of momentum. The ring has a radius of 15 centimetres. The centre of the ring is 2 metres from the wall. The child throws the ball with a mass of 0.058 kilograms towards the wall. The ball is instant normally on the wall with a horizontal velocity of 7.2 metres per second. The ball is in contact with the wall for 52 milliseconds before rebounding, normally with a horizontal velocity of 3.6 metres per second. What a mouthful. Calculate the average magnitude of the force. Okay, another exam tip. Whenever you see average force, you must start thinking about impulse. It's one of the very few places in physics where we start talking about average force is when we're looking at the idea of impulse. So whenever you see the words average force, consider the words impulse. Let's get on with the Solve Smart method. The first thing we'll do is section. Find the section of the data booklet that relates to this question. I've given you a few hints here. We saw the word rebound and I said whenever you see that word, think about momentum. I've also seen the words average force and I've said to you whenever you see those words, think about impulse. So you want to head to the part of the data booklet that deals with impulse and momentum. The next step of the Solve Smart method is symbol. So write all the data down on the left-hand side with the associated symbol. The radius, distance from the wall, mass of the ball, the initial speed of the ball as it hits the wall. And, this is an interesting point for vector motion. Momentum is a vector, so we want to choose a direction as positive. So let's say anything that goes to the left is positive. So we're going to say the initial velocity of the ball is positive. The final speed of the ball after the rebound is 3.6 metres per second. It's now moving to the right, which means that it's a negative. So we're going to call that negative 3.6. And the time over which this rebound happens is 52 milliseconds. So 52 times 10 to the minus 3 seconds. The next section of the Solve Smart method is to set up the correct equation. So you go to data booklet and find an equation that matches this selection of data. And the equation we're going to look at is for impulse. It is average force is equal to mv minus mu over t, or you might know it as the change in momentum over time. So we're going to take the data from the left-hand side and we're going to substitute it in. Remembering to put in our minus where appropriate. We've set up, we've substituted, now we solve and we come up with newtons. Let's look at sig figs. Go back to our data. This is two significant figures. This is two significant figures. Everything is pretty much two significant figures. So we want to give our answer to the maximum of two significant figures. Head back down and we write F average is equal to 12 newtons. And if you're being picky, I probably would have put that line above the F going forward because that just means average. And you'll notice I've missed out the sign there because it says calculate the average magnitude. It doesn't need to know the direction. So you don't need to put the minus in the final answer. Question 4. The brakes of a car of mass, 12,000 kilograms, are being tested on a track. The driver sees a hazard and applies the brakes. The graph shows the variation of the velocity of the car with time t from when the driver sees the hazard to when the car stops. Calculate the acceleration of the car when the brakes are applied. It's very clear the brakes are applied at this point here. So we're interested in everything to the right of this line. Using our Solve Smart method, we'll go to the section of the data booklet that we're interested in. And because this is a straight line, it's constant acceleration. Constant acceleration means Suvat equations. So we're going to head to the section of the data booklet that deals with the equations of motion. The next thing we want to do is write down the symbols on the left-hand side. We know that the final speed is equal to 0. The initial speed, we're going to read that off the graph, and that is 18. And we're going to give that 1 decimal place. The time taken for it to decelerate is the time between here and here, which is, that's 3.4, and that is 0.7. So the time between those two is 2.7 seconds. And we want to know what the acceleration is. Let's head to our data booklet and set up the correct equation. Well, the correct equation we're going to use in this case is A equals V minus U over T. Then we're going to substitute. So final speed is 0, initial speed is 18, divided by T. And then we're going to solve. A is equal to minus 6.6 recurring. Now 6.6 recurring insinuates that 6 goes on forever. And that's far too many significant figures. The least amount of significant figures in this data is 1, because we're looking at V is equal to 0. That's one significant figure. However, it doesn't seem reasonable to give one significant figure here. We can, as a rule, go up to one significant figure above the least significant if we need to. So we're going to say our answer is equal to 6.7 meters per second squared, and it's minus. It's minus because it's decelerating. So we'll underline that to show that's our final answer. B, calculate the average braking force while the brakes are applied. We see the word average, we see the word force, average force. I think we're going to be looking at impulse. So we head to the section of the data booklet that applies to this question. It's impulse. Then we write down the symbols on the left-hand side. We want to find out what the average force is. We have mass is equal to 1,200 kilograms. And we have the rest of the data up there. Then we set up the correct equation. The correct equation for impulse is this. Then we substitute. I'm substituting it in the data from the left-hand side. The initial speed is 18.0 divided by the time taken, which is 2.7. And we solve. So the average force is equal to minus 8,000. And that's right on the nose. The answer is exactly minus 8,000. And the minus, of course, means it's a braking force. It's in the opposite direction to the way that the car is travelling. So we underline that to say that's our final answer. C, calculate the total stopping distance of the car. Let's go back up to the graph. The stopping distance, or the distance, is the area under the graph. So we have two options. We can calculate the area of this rectangle, number 1, and the area of this triangle, number 2, add them together and that gives us total stopping distance. That's how to do it with the graph. Or you can just do it using the equations. Let's do it with the equations. So before the brakes are applied, it's travelling at a constant speed. So the distance is equal to speed times time. So the initial speed was 18 times the time it was travelling at a constant speed was 0.7. So the distance it travelled before the brakes were applied is 12.6 metres. After the brakes are applied, it's decelerating, so we're going to use the Suvat equations and we want to find out what S is. So S equals question mark. Let's use S equals U plus V T over 2. That gives us 18 plus 0 times T, which was 2.7, divided by 2. That S is equal to 24.3 metres. So the total distance, the total stopping distance is 12.6 plus 24.3, which gives us 36.9 metres. Are we giving our final answer to, we need to give it to two significant figures. So the total distance equals 37 metres to two significant figures. The reason I'm giving to two significant figures, I'm sure you're aware, is that this data here on the graph is all two significant figures. And the final part of question 4, D. Calculate the work done by the brakes to stop the car. We want to work out what work done is. We head to the data booklet that deals with work done, and we have symbols. We have F, which is the average force. We've worked that out earlier, 8,000. We have the distance travelled, which is done when the brakes are on. So that was 24.3 metres. And we head to the data booklet to find out our equation setup. Our correct equation is work done is equal to Fs cos theta. This cos theta element is to take into account if the braking force is not in the same plane as the direction that the object is travelling. But in this case it is, so cos theta in this case is equal to 1. So what we're really looking at is W equals Fs. F is 8,000, we're substituting now, times S, which is 24.3, the distance travelled while braking. That gives us an answer of 194400. We're not quite there yet. We want to get to the right amount of significant figures. That would be 2. So W equals 190,000 joules to 2 significant figures. Question 5. A swimming pool designer investigates the depth D below a water surface reached by a diver when diving from a height h above a water surface. The designer models the diver as a uniform wooden cylinder. The experiment arrangement is shown below. The cylinder is released from rest from a trapdoor. The base of the cylinder is at a height of h equals 0.3 metres above the water surface. Calculate the speed of the cylinder just before the base hits the water. Ignore air resistance. Do you remember my exam tip from earlier? If it says ignore air resistance, you're looking at Suvat equations or projectile motion. Given we're only in one direction here, it's just down, we're looking at Suvat equations. And that helps us with step 1 of the Solve Smart method. Head to the part of your data booklet that has Suvat equations or the equations of motion. The next step is to write the symbols down. Well, U equals 0. S, which is our height, is equal to 0.3 metres. Acceleration is acceleration due to gravity. It is in free fall, so we're going to put 9.8 there. Time, we don't know, but we do want to know what the final speed is. So we head to our data booklet and help us set up the correct equation. And in this case, the equation we're going to use is v squared equals u squared plus 2as. Then we substitute in our data from the left-hand side and solve. V squared is equal to 5.886, which means v is equal to the square root of that, so 2.426. We then finally want to give the right amount of significant figures. This is 2 significant figures. Acceleration due to gravity is 2 significant figures. So we'll give our answer to 2 significant figures. Our answer is v equals 2.4 meters per second to 2SF. Question 6. A footballer kicks a stationary ball of mass 0.45 kilograms towards a wall. The initial speed of the ball after the kick is 19 meters per second and the ball does not rotate. Air resistance is negligible and there is no wind. So air resistance is negligible means we could be looking at suvat or projectile motion. Let's see what else is going on. The player's foot is in contact with the ball for 55 milliseconds. Calculate the average force. So we're looking at impulse that acts on the ball due to the football player. We head to the section of our data booklet that deals with impulse. Then we write the symbols down the left-hand side of everything we're given. The initial speed of the ball is 0 because it's a stationary ball. The mass is 0.45 kilograms. The speed after it's been kicked, which is actually, in fact, our final speed, is 19 meters per second. The time for which it's in contact is 55 milliseconds. It's time to the minus 3 seconds. And we want to know what the average force is. Next, we set up the correct equation. Our equation setup is this. We've seen this before. And then we substitute our data. 0.45 times 19.0 minus 0.45 times 0 divided by 55 times 10 to the minus 3. Then we solve and it gives us the average force is equal to 155.5. But then we want to check significant figures. This is 2 significant figures. This is 2 significant figures. This is 2 significant figures. What are we going to give our answer to? It's not rocket science. We're going to give it to 2 significant figures. And we're going to underline it. The solve smart method comes through again. B. The ball leaves the ground at an angle of 22 degrees. The horizontal distance from the initial position of the edge of the ball to the wall is 11 metres. Calculate the time taken for the ball to reach the wall. We want to find out what time is. We're dealing with horizontal distance now. So we want to think about speed equals distance over time. We don't want to be thinking about suvat equations anymore or equations of motion because nothing's accelerating. So that's the equation we want to be thinking about. So that means we have the angle, which is 22 degrees. We've got the distance, and we're not going to write S down here because I tend to think S is for the vertical distance. It's 11 metres. So we're going to set up the right equation. We want time is equal to distance over speed. We know the distance is 11, but the speed, what's the horizontal speed? The horizontal speed is going to be UH cos theta. So substitute in 11 divided by 19.0 cos 22, which is 11 divided by 17.6, and that gives us an answer of 0.624. And of course, we want to give that to two significant figures. Time is equal to 0.62 seconds. Question 7. An elastic climbing rope is tested by fixing one end of the rope to the top of a crane. The other end of the rope is connected to a block which is initially at position A. The block is released from rest. The mass of the rope is negligible. The unextended length of the rope is 60 metres. From position A to B, the block falls freely. At position B, the rope starts to extend. Calculate the speed of the block at position B. So from here to here, it's in free fall. And if it's in free fall, we're looking at acceleration due to gravity is 9.8. And we're looking at this using the equations of motion or the Suvat equations. So we want to head to that section of our data booklet. Let's write down the data we have. The initial speed is 0. We want to find out the final speed. The acceleration is 9.8 metres per second squared. We know the distance is 60 metres. And we want to find out the speed. Okay, head to the data booklet. We set up the correct equation and we're looking at v squared equals u squared plus 2as. Let's substitute in our data. Let's solve. So v squared is equal to 11772. And then finally we want to look at the significant figures. This is given to three significant figures. Okay, so let's do three significant figures. To square root gives us an answer of 34.3 metres per second. And that's to three significant figures as the data is given. Final calculate question. A student uses a load to pull a box up a ramp at an incline of 30 degrees. A string of constant length and negligible mass connects the box to the load that falls freely. The string passes over a pulley that runs on a frictionless axle. Friction acts between the base of the box and the ramp. Air resistance is negligible. The load has a mass of 3.5 kilograms and is initially 0.95 metres above the floor. The mass of the box is 1.5 kilograms. The load is released and accelerates downwards. The vertical acceleration of the load downwards is 2.4 metres per second. Calculate the tension in the string. Okay, we want to identify the correct section of your data booklet. We're looking at the forces section. Maybe there's a formula for tension or pulleys. You're looking at forces. Certainly something near Newton's second law, like F equals ma. Then we're going to write down our symbols with the data on the left-hand side. We're looking just at the load right now. We know that the acceleration is 2.4 metres per second squared. We know that the mass of the load is 3.5 kilograms. We know that it's a height of 0.95 metres. And we want to know the tension in the string. Okay, let's try and draw a diagram and see if that helps. So we've got our box here. We know that it's accelerating downwards. So there's a force accelerating downwards, which is weight. And that force is bigger than the force acting upwards, which is tension. And the resultant force, which is weight minus tension, is the force that's causing it to accelerate. So weight minus tension equals the net force, which is equals to ma. So we're going to use the equation mg, which is weight minus tension, equals ma. And we're going to rearrange it for t. So mg minus ma equals t. And I've just swapped those two parts around in the equation. So tension is equal to mg, which is 3.5 times 9.8, minus ma, which is 3.5 times 2.4. Substitute in the data, and now we're going to solve. So 25.9 935. And we're going to give it to the correct amount of significant figures. T is equal to 26 newtons. Why am I saying two significant figures? Well, I think we've got the hang of it by now. That's two significant figures. That's two significant figures. So is that. And so is that. So our answer would be to two significant figures also. And we'll underline for our nice examiner. I hope you found this idea of working through calculate problems useful. I hope you've started to see how you can set out your working clearly so that the examiner understands what you're doing and you can obtain full marks every time.